Great, thank you. So hello everybody. So in this last talk before a coffee break, I would like to mention one interesting outcome of the ad hoc survey, possibly quite unexpected one. So I'm not presenting only my own work, but there have been lots of people involved. So I hope they are all listed and I did not forget anybody. So let's dive directly in. So in this talk, we are going to look at the Orion Nebula cluster. It's a quite special cluster because it's the closest star-forming, it's a part of the closest star-forming region that has formed, at least very recently, massive stars. So we don't know if there are some forming just now, but there are still O stars, and it's the closest star-forming region to us. And what is also a nice thing about it is that you can actually see it with your own eyes. So if you go outside in the winter, you can actually see it just below the Orion belt. Now in the numbers, it's between 1 and 3 million years old. It's only 400 parsecs away from us, which is exactly at the edge of the abilities of the Gaia, where we get also decent radio velocities. It's quite compact, around 1 parsec in radius, and it hosts around 1,000 star masses in stars. Now, it's extremely well studied. So there is more than 2,000 publications focusing just on this region itself, which I thought was quite remarkable. And as a student, I was quite confused. Why would anybody make a survey and actually look at it again? But it's good that actually it has been done. So because of the proximity and the properties and also how well studied this star cluster is, it has been considered a benchmark for young star clusters, but also star cluster formation and evolution. So apart from looking at how massive star clusters are or how extended, one very useful thing we can check is basically star formation history of a cluster. So here you can see it depicted very simply. So on this axis is the time, and here is the number of stars formed. There are multiple ways how we can actually do this for star clusters. So in the case of the Orion, there have been multiple studies in the past, also in the using the HST data, looking at the central region where it's very crowded and difficult to actually pinpoint and resolve the stars. And what you can see here is pretty much this single burst of star formation that happened fairly quickly on the time scale of a few million years. And that's it. Now, is it something that we understand? Is it something that we are all happy with? So if we try to do a simple experiment in our mind, how actually star clusters could form and what processes are involved. So here I will be showing basically a large molecular cloud, and you can imagine that there is a compact region in it, which is compact enough to form stars. Now, if these conditions are right and this happens, then on here we have the star formation history, and we can see that the number of stars formed is going to go up. And we will form low mass stars, high mass stars. We can discuss which will form first, and this of course will have an effect, because once actually massive stars appear, they have very strong feedback in forms of wind and mainly the UV radiation that basically dissociates and destroys and sweeps away the star-forming material. So when they appear fairly quickly, the star formation is truncated and we end up with basically naked star cluster. So this is great because this star formation history is exactly what we have seen in the Orion Nebula cluster. So we should all be happy because we understand what we see. And that's great. However, one of the results of the ad hoc survey is a paper with this title, which is already quite leading the message. A Tale of Three Cities, OmegaCam discovers multiple sequences in the color magnitude diagram of the Orion Nebula cluster. So after 2,000 papers, the 2001st, look at the Orion Nebula cluster again with only 2.6 meter telescope. Look at the bigger region and actually discovered something quite unexpected. So what did they see? So this is a plot from the discovery paper. Here you can see the color magnitude diagram, something you have seen here already many times. And you can see isochrone here. And then you see that there are still stars pointing here in further into the younger direction. So what you can see on this plot is the rectified basically all of these sequences are rectified based on this isochrone, and then on this plot they are all merged into histograms. So in this quantity, this difference in colors is basically a proxy of a relative age, and here you can see a number of stars that formed. So basically, this shows you a proxy to star formation history. And it looks quite different from what we have seen before. So instead of a single burst, there are actually 3 peaks. Now, of course, we were curious what we can learn from a Gaia data. So we looked at it also when the Gaia data release 2 was online. With Gaia, this is quite challenging. We were very happy to also have the ad hoc omega gamma photometry, because the central region is very crowded, so it's a challenge for Gaia. But we could basically, despite that, we could recover the same behavior, even though we lack the completeness in the very central region. Now, probably some of you who are familiar with the color magnitude diagrams, you are wondering, but maybe these are all unresolved binaries and unresolved equal mass triples. That's, of course, a very valid point. So Beccari et al. Already looked at it in quite some detail and tried to understand if they could explain this behavior by actually having equal mass binaries and triples, and concluded that they would need very odd period distributions in order to reproduce these. Moreover, we tried to do all sorts of filtering in the Gaia data that we could use, so spurious targets, Ruve-like at the time in the DR2 there was no Ruve, but Ruve-like quantifiers. We removed everything we could, and the peaks did not disappear. So, in a nutshell, we are dealing with the situation, and on top of that, the stars that do belong into the distinct peaks have other differences as well. Maybe the most remarkable one is that they have a bit different spatial distribution. So the oldest population, based on the isochrone, is most dispersed along the star-forming region, and the youngest is the most centrally concentrated, which is another evidence that points towards the fact that there have been 3 bursts of star formation in the Orion Nebula cluster that happened on a very short time scale within basically 3 million years. Now, I have spent quite some time discussing how we perfectly understand why we expect a single burst of star formation, because once the O stars appear, then there is basically not much to do because they disperse the gas, and how could there be actually 3 bursts? So it is now quite a conundrum. So in the next few minutes, I would like to show you a possible explanation to this situation. So in order to try to understand it, we need to look again at the bigger picture, but not only in the stellar content, but also in the gas content. So what you can see here is a sketch, but it's based on the ALMA data and ALMA paper of Alvaro Hacar, who studied in quite some detail the star-forming filaments in the Orion star-forming region, and noticed that there is basically filament that feeds gas directly into the Orion Nebula cluster. So this is the first clue that we need to consider. And then the second is going to be the fact that star clusters are actually dynamical systems. So we cannot forget that. So let's start actually with the filament. So we have the filament, there is inflowing material, which actually create perfect conditions for star cluster formation, because there is a pressure, there is a density, there is fresh material from which we can form stars. Now, this happens, and exactly as I was explaining before, we will have stars also, some of them along the filaments, but once the massive stars appear, they start to disrupt everything that is around them. So most likely truncating the star formation. And then there is nothing we can do. If this situation would be static, then we would only have a single burst of star formation as we expected before, because within 1 million years, there would be such a gigantic hole from all the UV flux that would be impossible to form any new stars. However, we have done quite a number of N-body simulations, and under certain conditions, there is actually quite a large probability that the O stars can be ejected from star clusters, especially from star clusters that are ONC-like star clusters, because based on the size, we only expect a handful of stars to form in the initial burst. And as we know, O stars form in the binaries, quite likely, and then once they're in the binaries, if the cluster has initially large density, it's quite likely that there is going to be a triple interaction, which are chaotic and unstable and can lead into the ejection of the systems. Now, if this happened in the Orion Nebula cluster and the massive stars were ejected fast enough before they managed to disrupt significant part of the filament, then the matter can flow back in, maybe not exactly at the same point, but the filamentary inflow can be restored, and we can form second populations of stars exactly in the center. Now, again, n-body simulations, n-body interactions can kick in, and the massive stars can be ejected, and the situation can go on and on until, for example, they don't. One O star would stay, it would dissolve significant part of the filament, and the formation would be over. Now, this scenario, while is still done using very simplistic simulation, can account for the presence of this tree population in the Orion Nebula cluster, so the formation of 3 bursts within 3 million years. And it also accounts for the difference in the spatial arrangement. Let me go back to the sketch, because basically what happens is that during the ejection and overall during the star cluster evolution, if there is a feedback and mass loss, then there is a change in the gravitational potential, and there is going to be expansion along the filament. So we actually expect exactly the oldest population to be the most expanded and the youngest to form in the central region again. We have looked into the literature. We haven't done a follow-up study by ourselves, but maybe this is something that should be looked at in more detail. But there is a report of actually quite old stars that have been ejected from the Orion Nebula cluster in the past. So this is also in agreement with the formation scenario using the filament accretion and the dynamical processes. Now, currently, there are actually massive stars in the Orion Nebula cluster, and the size of the cavity and the ionizing flux is actually predicting that the third population is currently forming. So this has some consequences. So let me just very quickly show you one plot that we did with the Gaia DR3. So there is nothing unexpected. We could confirm all the previous results, but for the first time, we could start looking at the kinematics of the 3 populations. So on this axis, you can see outflow velocity that has been estimated for the 3 populations that we have found. Here is a 0, so nothing crazy is going there. But you can see that the old population is outflowing with a very slow velocity as expected, and then the young population is actually still contracting. So the youngest population is still a bit unclear because it's only a handful of stars that we can use for this type of analysis to be sure that they are members and there is no contamination. And while this is not exactly in the agreement with the scenario I presented you before, it is definitely something that we are going to look into more details. So in the nutshell, the takeaway before the coffee break, I wanted to say that even the most studied part of the universe can surprise us. And sometimes we do not need a bigger telescope, but we need to look at the bigger picture. Maybe this is something to mention in the survey meeting in the era of the JWS team. Now, the filaments and larger scales, they need to be considered when we talk about star formation studies. And we should not forget the star dynamics and multiple star systems, because they can play a crucial role when we look at the formation evolution of star clusters. And in the case of the Orion Nebula cluster, might even determine whether star cluster forms multiple bursts or not. Thank you.